So, welcome to another lecture. In this lecture, we'll be doing extraction and corrosion of metals. This lecture is part of the series of lectures that I'm doing on Chemistry 0620 course. Now, in all these lectures, in all these series of lectures, what I've done is I have taken board papers from IGCSE 2025 papers. So, all the questions have been taken from the 2025 papers. You will see when you are going through this lecture, you will see these uh, the reference to the particular paper that I've taken the question from. So, extraction and corrosion of metals. See, I have divided this into three parts, and that is what I'll suggest that you can take. The first part, which is the easiest part, is the corrosion part. Corrosion part, the important question is about galvanizing. This is the easiest part, very easy to understand. Now, in this second part and the third part, there is extraction of iron and aluminium. Now, they have few of the questions, few of the students find difficulty in remembering all the all the equations that are there in the extraction of iron. So if you look at your textbook, you will have this kind of diagram, and there'll be series of these equations which will be there. So few of the students get very overwhelmed when they see all these equations. They see a diagram like this. My only suggestion to you would be that the first time you will see all these equations, you will get a bit jittery, but you have to revisit these equations again and again multiple times. Just have a look at these multiple times, say maybe once in 2 or 3 days, and slowly they start making sense. Because this happened to a few of my students. Then the second topic, in the extraction of iron, in the extraction of aluminium, the difficulty is that this is how the extraction of aluminium takes place. It's a fairly simple process, but then again, if you are not aware of the electrolysis, if you don't understand the nuances of electrolysis, then this might become difficult for you. But my suggestion to you would be that if you put some effort, then these will these will be a bit easier to tackle, because these are important topics. Every year, questions are being asked on either on iron or aluminium or galvanizing. So without further ado, let's start. So I'll be doing first questions from galvanizing, then I'll be taking the questions of iron, and then I'll be doing the question from aluminium. All the questions that I'll be doing would be from the 2025 papers, and so this will be a sort of revision. I won't be going into much of detail, but I'm trying to cover all the important things which are required. So let's start. Before I start, I'll just briefly take you through the topic. So basically, it's rust prevention. You should know the formula for rust. It is hydrated iron 3 oxide. If you look at your textbook, they will have mentioned a formula like this. It's a good practice to understand, to know the formula of rust. Then for rust prevention, we have barrier methods in which you can paint, oil, grease, plastic coating. So basically, what you are trying to do is keep iron away from oxygen and water. But the problem with these methods is that with time the paint will wash off, the oil greasing might lessen, plastic coatings might get affected. You can also try electroplating, but again here also if there are scratches, then the problem would be there. So for that, to tackle these, the other thing that we can do is we can galvanize, or we can have a sacrificial protection. And what I'll suggest is go through these topics from your textbook, and they are fairly easy to understand, not much of a problem. The only request to you would be, before you start, because there is an interdependency, so you'll have to understand the reactivity of metals. The topic that you should know before you start this topic is reactivity of metals, that how the reactivity differs. And the second thing that you should understand is you should understand electrolysis. You should understand electrolysis, because in electrolysis, if you have gone through electrolysis, you will understand that in the electrolysis chapter, one of the important topic is a question on electroplating. So you can refer to my electrolysis lecture. So there we have done electroplating questions also. Okay, so first question which is asked from corrosion is galvanizing prevents iron from rusting. Which statements about galvanizing are correct? So galvanizing involves coating iron with silver. No, it's not coating with silver. Galvanizing prevents oxygen and water from contact with iron. Yes, this is what happens. Galvanizing works because metal coating loses electrons more readily than iron. Of course, what we do is in galvanizing, we use zinc metal. We cover the iron with zinc metal. And because zinc is more reactive than iron, so, between zinc and iron, zinc is, sort of happier to donate electrons than iron. So, uh, one way of looking at things is that, zinc almost, it's just a way of looking at the thing that zinc almost stops iron from donating the electrons and, the iron getting changed into rust. So that is how galvanizing works. Zinc is used. Why zinc is used? Because zinc is more reactive than iron. It is far more forthcoming in donating the electrons. So the answer to this question will be second and three only. Because coating the iron with, if this was written zinc here, then this would be correct answer. So let's move to the next question. Zinc is used to galvanize iron to prevent it from rusting. Which statements are correct? Galvanizing is an example of barrier method. Of course, it's a sort of barrier method because that is what I told you in the, before we started this topic, that what galvanizing does is that it covers the iron with a coating of zinc. So, like for barrier method, we can also use painting, oil and greasing, plastic coatings also, and zinc also. So if zinc is scratched, the iron will rust very quickly. No, that is not the case. The whole point of galvanizing is because even if it is scratched, zinc is always more forthcoming in donating the electron. It's more reactive. Galvanizing is an example of sacrificial protection. Yes, it's an example of sacrificial protection also because we are sacrificing zinc rather than iron. Zinc is more reactive than iron, so accepts no. Zinc doesn't accept electron; it donates electron. So our correct answer would be 1 and 3. So galvanizing can be considered to be an example of barrier method, also is an example of sacrificial protection also. Next question. I'm skipping all the question regarding iron and aluminium. I'll be taking that in the second and the third part of the lecture. So corrosion, an example of sacrificial protection is fitting zinc blocks to the outside of ship's steel hull. This statement explain why zinc is used to protect the iron in the steel lusting. Zinc is more reactive than iron, so it loses electrons more easily. So again, whichever textbook you are referring, they would have a photograph like this. So they have zinc bars here on the outside of zinc, where zinc is used as a sacrificial metal. You can also have magnesium also. So if you go through your textbook, they'll have a paragraph on this also. And I told you earlier also that this is an important topic. 1 or 2 questions come. Yeah. There's a small question here. Iron rust when in contact with air and water. Name one barrier method used to prevent iron from rusting. So you can use painting, you can use oiling, you can use plastic. Part of steel ship is protected from rusting using sacrificial, which is a more suitable. Zinc is a more suitable. Again, as I've told you before, you should understand the reactivity. Once you look at the reactivity of the metal, so for reactivity, you can have a look at the reactivity series in your textbook. They would have a reactivity series which looks something like this. So, if you compare iron and zinc, zinc is more reactive, so that is why. But if you look at copper, copper is less reactive than iron. So that is why copper doesn't work. Potassium, silver, potassium. The problem with potassium is that potassium is very, very reactive. So it's almost insanely reactive. So you can't take that. If you take silver, silver is less reactive than iron. So zinc is the optimal element to metal to galvanize. Okay. Which statements above use the sacrificial protection to prevent iron from rusting are correct? Copper is not used as because it is less reactive than iron. So, like I've just discussed, so you can't use copper because copper is less reactive than iron. So, how will it protect? Because we need an element which would be, more ready to give out electrons. So that is all. Magnesium is used as a sacrificial protection because it loses electron more easily than iron. Yes, of course. Magnesium can also be used, Again, refer to your textbook, whichever textbook you are, which is there uh, in your school is absolutely fine. So if you look here, magnesium can also be used. Underground gas and water pipes are connected by wire to blocks of magnesium to obtain the same protection. So magnesium can also be used. This is incorrect. Zinc is used as a second because it gains. No, that is not correct. Okay. Iron rust in the presence of oxygen and water. These statements about rusting of iron are incorrect. And hydrous iron oxide is produced. No, hydrous iron 2 oxide is produced. So that is why I told you that please have a look at the formula of rust also. So, and it is hydrated iron 3 oxide. You look, this is iron 3 oxide. So it is not 2 oxide, it is 3 oxide. Iron rusts more quickly when attached to a piece of zinc. Incorrect. Coating the iron with plastic prevents. Yes, of course, it prevents. But with time, due to wear and tear, the plastic wears off. Iron loses electron when it rusts. Yes, it loses electron when it rusts. So the correct answer would be 3 and 4. Metal X acts as a sacrificial metal to prevent iron from corroding. Metal X does not act as a sacrificial metal to prevent aluminium from corroding. What is X? That is why I'm insisting again and again that you should have an idea of the reactivity series, because then you will be able to understand far more. So let us compare copper, magnesium, silver, zinc. So I've written everything here. This is copper, this is magnesium, this is silver, this is zinc. All the metals that are mentioned in the question I have written here. Iron, I have written aluminium also. So metal X will go step by step. Metal X has a sacrificial to prevent iron. So we want to protect iron. Okay. X does not act as a sacrificial metal to prevent aluminium from corroding. So the metal X can't prevent aluminium from corroding. So aluminium would be more reactive than that metal X. So what is X? The metal X would be zinc. Because zinc cannot prevent aluminium from rusting. That because zinc is less reactive than aluminium. That is why. So our correct answer would be zinc. Hope this is making sense. So skipping all iron and aluminium questions, then we have name the process used to coat iron with zinc as a method of rust prevention. So the process which is used to prevent iron from rusting is using zinc is called galvanizing. When the zinc is coating is scratched, the iron does not rust. Explain why iron underneath the zinc does not react. The iron beneath the zinc doesn't react because zinc is more reactive than iron, and it is always more forthcoming. It readily is there to give electrons. So that is why. Yeah. So again, this is a question which is was asked, and again, what I'm trying to suggest is that this topic is a simple topic. It doesn't require much of cramming. Just requires you to understand how the reactivity series works. If you know how the reactivity series work, then you can go through this topic. Because see, the basic logic is that you want to protect iron from rusting. So the basic logic is, see, the one way is that you can avoid the contact of the natural elements, oxygen, water, from reacting with the metal. We are trying to prevent the contact. So you can do plastic coatings, etc. The second way that you try to do is that you use galvanizing methods. Galvanizing method makes sense because you have a more reactive metal which is ready to sacrifice itself rather than the metal that you are trying to prevent, which is iron. Here they have taken the example of magnesium, that how magnesium prevents the rusting of iron. Previously we have done zinc. So steel consists mainly of iron. Okay, iron rust when it reacts with water and oxygen. Absolutely. Shows magnesium block attached to the bottom of a steel board. Okay, magnesium does not completely cover the steel. Yes, it doesn't completely cover the steel. Yes, magnesium blocks provide sacrificial protection for the steel, correct? Now, again, look at the reactivity series. You have iron here, you have zinc here, and magnesium is far more reactive than zinc and iron. So, in a way, it is far more. It is also more suitable than zinc, so as to say. So, explain in terms of electron why magnesium is used as a sacrificial protection, because it is there to to give out electrons. So, and I mentioned the reactivity series also, so that you can compare between magnesium and zinc. Then the second question is, name a metal that cannot provide a sacrificial protection for steel. So, like we had done in a question before. So, for example, copper. Now, copper won't be able to prevent the rusting of iron because it's not very forthcoming in giving out electrons. So, metal that cannot provide sacrificial protection for steel is any metal that is less reactive, more noble than iron. Common examples include copper, tin, and nickel. These uh, these metals, because they are less reactive than iron, so they won't be working as sacrificial. They can't provide sacrificial protection for steel. So we have done with the corrosion and the galvanizing questions. These are the kind of questions which are asked, and let's move now to the extraction of iron question. And after that, we'll be moving to section of our lecture where we'll be doing the extraction of iron. So for iron, usually if you look at your textbook, they'll have given a diagram like this. This is a diagram of a blast furnace. They would have mentioned the equations also and the temperatures also. Now, before I start doing the questions, what I've done is I've simplified the things as much as I can. So that it is easier to have an overview of the extraction of iron. Basically, you will have a blast furnace like this. So blast furnace is about a 30-meter tall sort of tar. There will be three things which will be put in the blast furnace. So we'll have coke, is basically carbon. We will have the iron ore, and we'll have limestone. Now, the interesting thing is that the reactions would be taking place between these two entities. Now, the interesting thing to observe is that the limestone part is just there to remove the impurities uh, of the which come with the ore. So the main impurity that comes with the ore is silica, SiO2. So remember, this limestone part, it is just here to take care of the impurities which come with the ore. So let me show you the reaction of the limestone first. These are not balanced equations, so just take care of that because I've tried to simplify as much as I can. So this is a limestone. This on heating gets converted into CaO plus CO2. The high temperatures are there. So if you refer to your textbook also, we'll have temperatures to the scale of 1500 degree, 850, 750, 200. So these are the kind of temperatures we are talking about. So the limestone that you are adding, this converts into CaO plus CO2. Now this CaO, this reacts with the silica to form slag. This slag is drained off from the blast furnace. So the purpose of the limestone is just to remove the main impurity which comes with the iron ore. The main reactions are this coke will react with the oxygen which is supplied by the air. So C plus O2 forms CO2, then CO2 further reacts with coke to form carbon monoxide. This is the main reaction where the conversion takes place. In this reaction, the iron ore reacts with carbon monoxide to form iron plus CO2. I have told you this is not a balanced reaction. So I have tried to reduce the reaction in your textbook to this format. Now, my request to you would be, these kind of equations, the more often you keep revising these kind of equations, the better they get into your long-term memory. So let's start with the questions. So basically the questions that you will discuss now would be asked from these points only that I've just discussed in the last 4-5 minutes. So which process is used in the extraction of iron from hematite? Hematite is the ore of iron. Remember that. So it's a reduction reaction. See, this is a reaction which I was writing Fe2O3. This is a balanced reaction. So Fe2O3 here, as I've told you, this is not a balanced reaction. This is not a balanced reaction. So Fe2O3 plus 3O2 Fe plus 3CO2. So this is the iron that we get. This is the extraction of iron. Now again, when you are doing this chapter, you require a basic understanding of oxidation reduction, because the same would be required when you are doing the aluminium extraction also. So here, if you see, the oxidation number of iron here is plus 3, gets reduced to 0 when it converts into its pure form. So it's a reduction for iron. So which process is used in the extraction of iron from hematite? Reduction processes. Hope it makes sense. Let's move to the next question. Okay. Which equation represents the reaction that occurs in the blast furnace during the extraction of iron? So this is the reaction which takes place. As I've told you, this is the heart of the reaction which is taking. Yeah, another thing. Yes, same thing. Another thing that you can see is that these are the two gases which are given off. So these are the two waste gases which are given off. So here also a question is asked: what are the waste gases which are given off? CO and CO2, which get remain unreacted, they are given off. Okay, next question. Complete the following equation. I have completed the equation. Name the main ore. We have discussed hematite. State one reason why carbon is burned in the blast furnace. See, the carbon which is burned, because this carbon will give us the carbon monoxide. This is how the reaction takes place. So C plus O2, CO2, then CO2 plus carbon gives carbon monoxide. This carbon monoxide reacts with our ore to form iron, and CO2 is given off. So we have done this question. Name the solid compound that forms when limestone undergoes thermal decomposition. So this is a calcium oxide is the compound that forms when limestone undergoes thermal decomposition. Okay. As discussed earlier, all the aluminium and the corrosion based questions I have done. Corrosion I have done before. It's part 1, and aluminium I'll be doing after this. So I'm skipping them. Okay. Iron. Which equation represents the reduction of iron found in hematite in blast furnace? Again, the same equation. So very important equation as you. Okay. So blast furnace is shown. Iron is extracted from the core, from the ore. This is the air that you are supplying. These are the waste gases that are being removed. Slag is being removed as discussed before. Then we have A. A basically here represents molten iron. This is a question which I think this is a question being asked. Coke and iron are added to the top of the blast furnace. Name one other substance that is added to the top of the blast furnace. So limestone is added. PaCO3 is added here in the top of the blast furnace. So three things are added: coke, iron, and limestone. Coke and iron are added to the top of the blast furnace. Name another substance. Okay, name the substance that leaves the blast furnace at A. So iron leaves at A. Molten iron, which is found, leaves at A. Above that, layer of slag forms, which is removed. Slag is produced from an impurity of iron ore. Name the impurity in iron ore that is converted into slag. So silica, sand, is the main impurity. Name two substances that react to form high temperature in the blast furnace: C plus O2, CO2. So this is a high temperature reaction. Name two waste gases: CO2 and carbon dioxide, carbon monoxide are the main two gases that leave the blast furnace. So this is where the waste gases leave. Okay, same question again. We have already done this question. So these are the few questions that are asked in for iron, and again, what you need to understand is just reduce the reaction to its bare bones so that you are not overwhelmed by this topic. So let's move to the next topic, which is extraction of aluminium. For extraction of aluminium, as I've told you, you will require a bit of understanding of electrolysis. In this part of the lecture, we'll be doing the extraction of aluminium by electrolysis. The first thing that you need to remember is the name of the process. We'll be doing few questions about this, but before I start, I'll be just giving you a brief of the process of the electrolysis process. The first important thing is to please know the name of the electrolysis process. This is in respect. The name is in respect of the two gentlemen who formed this, who jointly discovered this process. So the name is very important. So in briefly, what happens is the first thing, the process happens in 3 steps, as is mentioned in your textbook also. There's a first important process. The ore of the aluminium is bauxite. First, it is treated with the sodium hydroxide. So this is a process which you have to, which you should know, because there are questions asked on the basis of this. We'll be doing a question also. On the basis of this point, a question has been asked. So bauxite is treated with sodium hydroxide in refinery to obtain pure aluminium oxide. So the pure alumina is formed in the first step. In the second step, what you do is that the purified aluminium oxide, the alumina, is dissolved in molten cryolite. So the cryolite, basically what it does is it lowers the temperature of the melting of aluminium oxide. Because if you refer to your textbook, you'll understand that alumina has a melting point of 20-30 degrees Celsius. But when we add cryolite, the temperature, due to the addition of cryolite, the melting point decreases to 900 to 1000 degrees Celsius. Now, how this helps us is that it basically uh, halves the cost of the electrolysis process. So this is the magic what cryolite does. And in your book, they have also mentioned the formula of cryolite, Na3Al6. So it will help you to remember this also. Now, Al2O3, see, the problem is that our Al2O3, aluminium oxide, is very stable. Because it is very stable, so when you want to extract aluminium out of it, you have to provide tremendous amount of energy. And that energy is provided by the electrolysis process. Now, it will help you to remember the conditions also. So 5 volt and 200 kiloamperes is the energy which is required. The setup somehow looks like this. There are carbon anodes, and there is a carbon lining which acts as the cathode. So we know anox, red cat. So at anode, oxidation will be taking place. At cathode, reduction will be taking place. Remember this, because there are mixed questions which are also asked. The reaction that happen looks something like this. So this is a reaction for aluminium, and this is a reaction for oxygen. Now, if you look, electrons are being gained, rig. Reduction is happening. Red cat is the mnemonic that we use. So this will be happening at the cathode. So this reaction will be happening at the cathode, which implies that this is our cathode. So aluminium would be collected at the container. This is the reaction. This is the loss of electrons. Loss of electrons is oil. Oil is loss of electrons. Anox. So I'm just referring to the mnemonics. Anox, red cat, oil, rig. So at anode, oxidation takes place. At cathode, reduction takes place. Oxidation is loss of electrons. Reduction is gain of electrons. So these are the mnemonics that I use, that I've explained in detail in electrolysis also. So we come back to the second reaction, which will be happening at the anode. So reduction has happened at the cathode. Here, oxidation will be happening. Oxidation is loss of electrons. So of course, loss of electrons is happening. So this is oxidation is loss of electrons, and this is happening at oxidation is happening at anode. So now, if you look closely, during oxidation, oxygen is being released. Oxygen is being released. This oxygen reacts with the carbon electrodes. The temperature is also pretty high. So this oxygen reacts with the carbon electrodes, and CO2 is formed. So this is another important question. That the question which is asked is why anode has to be periodically changed. the anode has to be periodically changed, because oxygen which is released reacts with the electrode itself and forms CO2. So these are the few things that you need to remember before even we start doing the question. And if you want a detailed treatment, then you'll have to refer to your textbook. Now let's start the questions. Now, what you will find is that only these things are being asked in the exam. We'll be doing questions and you'll understand. So, which equation represents the reaction at the anode? See, at anode, this is the reaction which happens as we have just done. So, this is the reaction. This is the reaction we just discussed. So, oxygen is released. So, oxygen is released at the, and this oxygen which is released, this reacts with the carbon anode. Okay, next question. When aluminium is placed in dilute HCl, there is no reaction. When zinc is placed in dilute, which statement correctly describes aluminium is coated with the layer of aluminium oxide? So actually, this question is from another chapter, but I thought of including this so that you understand that once aluminium has reacted with the oxygen from the environment, a layer of Al2O3 is formed, which is very unreactive, which doesn't allow aluminium to react. This question is not from the chapter. It's okay. So aluminium is extracted from its ore by electrolysis, which is what is the role of cryolite to lower the operating temperature. Next, aluminium is extracted from aluminium oxide by electrolysis. Ionic half at one of the electrodes, Al accepts electrons to form aluminium, which row cathodes, which row describes the change in oxidation of aluminium and the type of reaction at the electrode. So if you see the oxidation number is +3, changes to 0. So reduction in the positive charge is happening. So, or reduction in the oxidation number is happening. This is a reduction which is happening. Rig, reduction is gain of electrons. Red cat, this reaction happens at the cathode. And what we have seen is in electrolysis, whole of the container acts as a cathode. So these are almost the questions which are asked again and again, and they are based on the process only. The main points of the process, any process that you are studying. Aluminium is manufactured by electrolysis of aluminium oxide. Okay, name the main ore of the aluminium. It is bauxite. Name the substance mixed with aluminium oxide to reduce the temperature. It's cryolite. This is the formula. Explain why molten conducts electricity, because the Al2O3 aluminium oxide is a ionic compound. Once you have molten it, it breaks itself into its ions. That is why it is able to conduct electricity. Al3 plus oxygen ions. Basically, the structure breaks due to melting. Contains information about the process which take place at the anode and the cathode. So this is a reaction which is happening at anode, and at cathode we understand that this is a reaction which will be, this is the Al plus 3 electrons forms aluminium. This is a reaction which will be happening at, write it here, Al plus 3 accepts 3 electrons. Al. Now, if you see, there's a mismatch. Okay, so I'll balance this. So if you see 2O2, O2 plus 4 electrons, so there should be 4 electrons here. Now, if you see carefully, I'll again write it here so that you can understand this correctly. So 2O2 gives O2 plus 4 electrons, and Al plus 3 electron forms Al. Now these, here there are 4 electrons, here there are 3 electrons. So this needs to be balanced, and that is why we multiply the first one by 3, the second one by 4, so that we have a equation like this. 6O negative gives 3O plus 12 electrons, and 4Al plus 3 plus 12 electrons gives 4Al. Now, if you see electrons, they are balanced on both sides of the equation. Write the number of electrons needed to balance the ionic half equation for the reaction at the anode. So this is just for your understanding. Just for your understanding that the number of electrons actually should also balance. This is not what is being asked in the question, but I just want to tell you that the number of electrons in the ionic half equation should also balance. But here, write the number of electrons needed to balance the ionic half equation for the reaction at the anode. These are the number of electrons which we require. I hope you have understood that this is not being asked. This is an additional information that I am giving. Write the ionic half equation of the reaction at the cathode. I have written it. State why the process at anode is oxidation. Already explained. Oxidation is loss of electrons. So here loss of electrons is happening. So that is why oxidation. So oxygen is formed at the anode. Explain why the main gas given off at anode is carbon dioxide, not oxygen. I already explained that the oxygen which is formed reacts with the electrode itself to form CO. So this is a gas which is. Why aluminium is used in food containers? As I've already told you, a layer of aluminium oxide is formed, which is very stable. That is why, when we are doing electrolysis, so this stable layer of aluminium oxide is helpful also because in a way it helps us make food containers. But the problem is when we have to extract aluminium, a lot of energy is required. Move to the next question. So this is the question which I told you. Aluminium metal is extracted from its purified ore by electrolysis. In electrolysis, we use the purified ore because this is the second step. Which statement about the electrolysis in the process is correct? The electrolysis purified bauxite dissolved in molten cryolite. So the electrolyte is pure molten bauxite only. This is incorrect. Electrolyte is purified molten cryolite only. This is incorrect. Electrolyte is purified cryolite dissolved in molten bauxite. This is incorrect. Electrolyte is purified bauxite dissolved in molten cryolite. This is perfect. And why it is written purified bauxite? Because as I have told you, the before the bauxite is sent for electrolysis, the first process it undergoes with sodium hydroxide. So these are the questions which are asked in 2025 regarding the aluminium process. And I hope these three parts. So in the first part we did corrosion and galvanizing. In the second part we did blast furnace, iron, and in the third part we are doing aluminium. So I will be attaching this PDF with this lecture, and more or less this is a short revision of the chapter, and you will also understand the kind of questions which are asked from this chapter. So though it seems to be a difficult chapter, but as you would have understood, the questions which are asked once you have gone through the chapter, the questions are pretty easy. Repeatedly the same questions are asked. So thanks for watching. Hope this was useful, and best of luck for your